Bismillah ar-Rahman ar-Rahim. Welcome to Tahar Scholar. So we are today الاثنين 15 أبريل 2024 بالجزائر, or in English Monday the 15th April 2024 in Algeria. So this is the first tutorial of chapter 2 dedicated to Cramer's rule. The series will be subdivided actually in several parts. Each part is dedicated to a method or to a topic, a different topic. In this first part, we apply what we have already seen in the previous 4 lectures. So in the first lecture, we presented the problem and the methods we will study in this chapter, and we have also revised in detail the inner product. Solving a system of linear equation is actually equivalent to a linear mapping. And the linear mapping is based on the inner product of a matrix with the source vector, and we get the image vector. That's why we have revised the inner product. In lecture 2, we made a revision on matrix algebra. Namely, we have seen determinants, the identity matrix, the inverse of a matrix, and the rank of a matrix, the image space, the null space, and we have explained that the rank is actually the dimension of the image space, or the maximum number of columns in the matrix that are linearly independent. So the rank is important when the matrix is singular. When the matrix is invertible, the rank is equal to the size of the matrix. So in lecture 3, we have presented Cramer's rule as a theorem, and we have seen some examples. And in lecture 4, we have explained what is an adjugate matrix, and then deduced a formula for the inverse matrix using Cramer's rule. And then the second point, we have seen how to calculate the rank of a singular matrix using a minus. So this tutorial, we will apply particularly what we have seen in lecture 3 and lecture 4. If you have not seen yet the videos, I of course advise to watch first the 4 lectures about, I think, about 5 hours. The second lecture is a little bit longer. You can, of course, subdivide your watching time. You can subdivide it in parts. See the first section, make a pause, see the second section, and so on. And in the information box or description box, I have detailed the sections, what YouTube call chapters. So let's first see the series on the screen, and then we come back and solve the exercise. There are 2 exercises. Series number 2, Systems of Linear Equations, Tahar Scholar Channel, copyright 2023-2024, Tahar Jawad. I have started this channel on YouTube in September 2023. The module is Numerical Methods, and the date 23rd March 2024. I have written the series while I was preparing this chapter. So part 1, Cramer's rule. There will be, of course, more exercises when we progress in the chapter. So for this first part, we have 2 exercises. Very simple. Exercise number 1, solve the following system of linear equations using Cramer's rule. So we have 4 systems, 3 by 3, because we have said that Cramer's rule is best suited for small matrices, 2 by 2 or 3 by 3. We can also use it 4 by 4 and 5 by 5, but above that, it is really impractical. And after solving the systems, for each system, calculate the residual and then check whether it is indeed close to 0. We will solve only the first system, and give the results for the other systems. So, and I advise at least try by yourself to do at least one exercise. Don't be passive, just watching. Once you watch, after you watch the video, try to pick one system and solve it by yourself using Cramer's rule. The second exercise, we solve the same systems, but with a different approach. So solve every system with the previous exercise, but this time using the inverse matrix in the following steps. First, calculate the adjugate matrix edge of A. Then deduce the inverse matrix, A minus 1. And finally, calculate the solution using the inner product x equal A minus 1 dot B. This is not an efficient way, as I said in lectures. Better solve directly using Cramer's rule or Gaussian elimination. But here we are learning, just learning the other approach, the other method, using the inverse matrix, even though it's not efficient. And then the last point, compare the accuracy of the solution with the one obtained using the direct method in the previous exercise. The accuracy is almost the same, but here it involves more calculations. Now, for small matrices, it's okay, it's not a big deal. So let's go to our notebook setting and solve the exercises. Let's start with exercise number 1. We have the system. So we have our system, and the vector x is the unknown. The matrix A is given, and the vector B is also given. The image vector, the source vector. And Cramer's rule, if you remember in lecture 3, the components of the solution are given by xi is the determinant of A, matrix A, except one column is replaced by B, and that column is the ith column. So matrix A with vector B at the ith column. Calculate its determinant, and we divide by the determinant of A. The determinant of A must be different from 0, otherwise the method will not be applicable. So this is for each component. For each component I from 1 till m, here till 3. So this is Cramer's rule, very simple. So we have to calculate, first of all, the determinant of the matrix, of the mother matrix or the system matrix, delta, which is by definition the determinant. So here we choose the first row to calculate the determinant. So we have 0, 3. We eliminate the first row and the first column, the row and the column containing the first element. So we get 1, so for the first element, we have a sign plus, then the second element minus, and then plus. The elements are on the first row, And the minors are obtained by eliminating the row and the column containing the element. So for the first minor, 103, 0, I have made a mistake. It's 1.9. Okay. So 103, 1.9, 1.9, and 0.5. For the second element, we have 0.5, 0.5, 0.1, and 1.9, 0.5. Okay, and for the third element, 0.5, 0.1, and 1, 0.3. Okay, and we do calculation of minor of a 2 by 2 matrix, very simple. You multiply the diagonal, 1 times 0.5 minus the other diagonal, 0.3 times 1.9. Or you work using the definition, the first element, its minor is an element. It's a matrix 1 by 1. And the second minus the second times its minor is 0.3. Same result. And we obtain here minus 0.002. We use 5 digits, but here we haven't done any rounding offs. It's exactly the number. Then the auxiliary determinants, a determinant for each component, as the definition. As the method, Cramer's rule. What Cramer's rule tells us, you have to build a matrix except the matrix A, using the whole matrix except the ith column. You replace it by B. Exactly what we will do here. So the first column, we reserve it for B, and the others from the matrix, from the mother matrix. So here 0.52, 1, 0.3, 1, 1.9, and 0.5. And here we put the vector. We go slowly, but because it's the first tutorial, and once you are familiar, it's very easy, very simple. When the matrix is smaller, 2 by 2 or 3 by 3, it's very simple to apply Cramer's rule. And the hard work is on the determinant, calculating the determinants. The hard work, it takes time, that's it. It's not hard. So the first elements of the row, and then we obtain the result. Let's do it again. Let's do it again for the sake of pedagogy. So minus 0.01. The element is negative, but the sign is plus. And it's minor. We eliminate the row and the column. So we have 1, 0.3, 1.9, 0.5. And then minus the element 0.52. And it's minor. We eliminate the second column, the first row. So we have here 0.67 minus 0.44 and 1.9, 0.5. And then plus, sign minus, plus, then minus, then plus. It alternates. And the element is 1. And the determinant, let's write like this for the elements. So we have 0.67 minus 0.44 and 0.3. So once we have that, we use calculator and we calculate the minors times the element, the minus times the element, the minus times the element, and be careful with the sign. And we find 0.03278. 0. Here also no round off. Delta, delta 1, we continue with delta 2 and delta 3. The second auxiliary determinant, we leave the second column. We reserve it for B. And for delta 3, we reserve on the third column. And we put the vector B, the image vector, the same, and the rest columns from the original matrix, matrix A. So and we don't have to do all the details. We just put the final result, because we have seen how to calculate the determinant several times. You pick any row, any column, and then you calculate the minors for each element of the row or the column you have chosen. And we find 0. Here also we use 5 digits. Along the exercise, we use 5 digits after the decimal point. But this is an exact number. It's not rounded off. So albeit we have chosen only 5. If you have chosen 3 digits, we have to round off, of course. So we have said that the method is sensitive to round off errors. Better work with 5 digits. And in this exercise, the numbers are exact. We didn't, even here, we didn't make, after 6 it's 0, 0, 0. We didn't make any rounding offs. So now that we have the auxiliary determinants, we divide them by the determinant of the matrix, of the mother matrix. Very simple. x1 is 0, 3 is 0.03278 over minus 0.00220, and we find the result minus 14.9. And for x2, and the third element, x3, and that's it. So now let's, because the exercise tells us to check the accuracy using the residual. The residual, by definition, is A, the inner product of A with the solution X minus B. So this is the approximate image minus the true image. Okay, and we find the result 10 times minus 16, and the other elements are different from 0. And we use only one decimal point because they are very small number. 10 to the power of minus 16 is almost 0. 1.7 and minus 1.3. So it's really very small. it is in the order of machine epsilon. The smallest, if you remember, we have seen that in the practicals on MATLAB, I think. Machine epsilon is the smallest positive number that the machine can store. Any number below that epsilon machine is 0. Okay, so there are actually 0 numbers. So it is almost the vector 0. So here we obtain very good accuracy, albeit we have used only 5 decimal, because we didn't make any rounding offs. Any. The results here for the determinants and also for the ratios here for the components are exact. We worked with 5 digits after the decimal point, but no rounding off. That's why the precision is really good. So that's it for the first system of our exercise. For the other systems, I just give the final result, and I advise you to pick any one and follow exactly what we have done with the first system and try to compare your result with mine. I use a calculator, of course, and don't be passive, just watching. Try to apply what you watch, what you are learning. So for the other systems, the second, the third, and the fourth system, I give the result, the auxiliary determinants, or the common determinant of the matrix, and the result. Okay, so take a look, and whenever you want, you can come back, pick a system and check. Now let's move to the second exercise. So in the second exercise, we solve the same system, the first system. We start with the first system, and I give the result for the other systems, like we did in the first exercise. But here we use another or a different approach. We calculate the inverse. So let's recall here the matrix. And the vector B. And first step, we calculate the adjugate matrix. So the adjugate matrix, as we have seen in the lecture, the adjugate matrix of A, any matrix, any square matrix, is defined by the cofactor of the transpose of the element. So the Aj A as the element Ij is by definition equals the cofactor of A Ji. Okay. So what we will do, we will calculate the minors, all the possible minors for each element. So we will have 9 minors, and then we calculate them by columns, and then we put them in the adjugate matrix by columns, by rows I mean. We calculate them by columns from the mother matrix, and we put them by rows in the adjugate matrix, along with the sign. So the minors do not include the sign. But the cofactor, we have to take care about the sign. The sign is very simple, plus, minus, plus. It alternates by rows or by columns. Okay, so let us first calculate the minors. M11 of the first element. We eliminate the column and the row. We get 1 times 0.5 minus 0.3 times 1.9. and M21, second element in the first column. We eliminate the second column and the second row and the first column. We get 0.52 times 0.5 minus 1 times 0.3. And we find minus 0.04. Here we find, I have my notes in front of me, minus 0.07. You can, of course, check the result with me or later with the calculator. So the third element in the first column is the element in the first column. We eliminate the third row and the first column. So this is the minor. 0.52 times 1.9 minus 1 times 1. And we find minus 0.012. So this is for the first column. We do the same for the second column and the third column. So I will put the result, the same technique. So we have here this is for the second column and for the third column. And we put the resulting numbers here by row in the adjugate matrix, along with the sign. Don't forget the signs. So this will lead to the adjugate matrix A, adjugate matrix of A, so let me check here the values. Minus, plus, minus, the values, plus, minus, plus. Okay, so this is for the adjugate matrix. And the inverse matrix is a piece of cake, because you multiply the adjugate matrix with the inverse of the determinant. So the inverse matrix is defined as we have seen in the fourth lecture. A minus 1, it's a theorem we have seen in the third lecture, is the inverse of the determinant of A. An invertible matrix, it has a determinant different from 0, with times the adjugate matrix. In our case, we have already calculated the determinant in the first exercise, and we have found the number minus 0.022. 5 digits after the decimal point, and times the same matrix here. Let's repeat it here again. This is our inverse matrix. So let us now see third step, the solution. The third step, we calculate the solution. We have the inverse matrix, so our solution X is the inverse matrix dot the vector B. It is the inverse image, or the image by the inverse matrix of the image vector. So the inverse image of the image. Okay? We replace a minus 1 by its value and b by its value. Very simple. We have we do the dot product of this matrix with the b vector, a with a minus 1 with the vector b, we obtain the following. So again, the determinant, the inverse of the determinant times the following vector. You can check very easily that actually this vector are the auxiliary determinants we have found in the first exercise. So let's write them here. Are the auxiliary vector, the auxiliary, determinant, beg your pardon, determinants are the auxiliary determinants, of Cramer's rule we obtained in exercise 1 for the system, for the same system, for the system number 1. So this is an important note. So when you perform the inner product of, not the inverse, this is the adjugate. Okay. And this is the vector B. When you perform the inner product of the adjugate matrix with the image vector, you obtained exactly the same values of the auxiliary determinants in a vector. For delta 1, delta 2, delta 3. You can easily check. So this is an important note. If you don't find the same result, you have made a mistake. And we obtain, of course, the same, because we are applying Cramer's rule actually. We obtain the same result, minus 14.9, minus 29.5, and 19.8. For the other systems, I will put the result, and you can check by yourself. You can pick any system, calculate the adjugate matrix, perform the inner product, and then get the result. Exactly the 3 steps we have done in this for this system. So let's see the result. So the result for each system, the inverse matrix, and the solution. You multiply the adjugate matrix, or you do the dot product of the adjugate matrix with the image vector, like we did with the first system. You obtain a vector containing actually the auxiliary determinants, and then the result. Same for system 3 and system 4. So always check that the adjugate matrix dot the image vector is equivalent to the auxiliary determinant we have obtained with Cramer methods. It is with delta I is the determinant of the matrix A with the vector B, the image vector, at the ith column. So for I from 1 till 3. And that's it for our first tutorial. Next time, inshallah, in next video, we will see a practical dedicated to Cramer's rule. And then afterwards, we come back to our chapter, to lectures of our chapter, and continue with Gaussian elimination. So see you inshallah next time. Peace.